This is the second of 7 videos on index notation and index laws. This one once again is revision from grade 8, revision on the first 3 index laws which you should be familiar with from last year. So let's look at our learning goal. What we're hoping to obtain here is that you can use your knowledge of index laws to simplify and solve different problems. So here's our first index law, which you should be familiar with. It's the multiplication law. Now you will recall that when you multiply numbers in index form with the same base, so we multiply them, we add the indices. That's very important. So this is the rule. A is our base, M is our index, A is our second number, and N is the second index. And we're multiplying them. So that means we use the first law. So when we do that, we add the indices. So when the bases are the same, you add the 2 indexes together. So here's an example. 2 times 4 times 2 times 3. We have the same base. Now what I'm going to do is show you how this works before we apply the index law to prove to you that it does actually work. From our previous lesson, we know that 2 to the power of 4 is equal to 2 times 2 times 2 times 2. That is 2 multiplied by itself 4 times. And 2 to the power of 3 is 2 times 2 times 2. 2 multiplied by itself 3 times. Now, look at that as a group together. We have 7 2's there multiplied together, so that means 2 to the power of 7. And we get the same result there as we would by adding those indices. So that's the proof of the rule. So here's an example we can work with. 5e to the power of 10 times 2e to the power of 3. Now these have coefficients, that is numbers in front of them. So here's our solution. First step, multiply the basic numerals separately, that is our coefficients 5 and 2. Add the indices where the bases are the same. So our 2 basic numerals are 5 and 2, so we multiply them. So I've separated them out to show you how you might do this. And our indexes are 10 and 3, so we're adding those together. So the solution to this problem is 10e to the power of 13, because 10 plus 3 is 13. Here's another example that's a bit more involved. So I've got 2 different bases this time, m and n, and a number of coefficients. Now you may recall from your knowledge of algebra that when there's no coefficient, that means 1. We're going to use that knowledge as we go through here. So the first step is that there's our 1. You may wish to rewrite them. This step's not totally necessary, but some students may find this useful. So here I've color-coded all of the coefficients of the numerals in blue. I've color-coded the base m indexes in orange and the n indexes in green. So they're the groupings we're looking at. So 7 times 3 is 21, times 2 is 42. We add 3 and 8 because it's the same base of m. And we add the 5 and 4 here because it's the same base of n. And when we get that, we get 42 multiplied by m to the 11, n to the 9. As we remember, we don't need those multiply symbols when we're using algebraic terms. Here's another example, once again, slightly different. And this is because we've got this x here without an index. You may recall that when there's no index showing, it has an index of 1. So this is what it actually looks like. So once again, if you like, rewrite them in order. So there's our coefficients, our numerals. Here's our x's, and here's our y's in blue. So 4 times 2 is 8. 1 plus 3 for the x's, 5 plus 2 for the y's, giving us 8x to the 4, y to the power of 7. Here's our second index law. The second index law is the opposite of the first law. The first one was multiplication, the second one is division. So that's division for the second law. When we divide numbers in index form with the same base, once again same base, that's the key, you subtract the indices. So here's our rule, a to the power of m divided by a to the power of n. They have the same base, we subtract the indices. This only applies if the bases are the same. And don't forget, instead of divide, we can write in fraction form, so that also represents a divided by a. So here's an example to show you why it works. 2 to the power of 5 divided by 2 to the power of 3. Once again, Split those into factor form. There's our green 2's, there's 5 of those multiplied together. And there's our purple 2's, 3 of them multiplied together. And what we're going to do is cancel them out. So we subtract the indices, but when you're dividing, what we're really doing is cancelling. There's 1 there, divided by that is 1. That 2 divided by that 2 is 1. That 2 divided by that 2 is 1. And we're left with 2 times 2. So if we look at that, we get 2 squared. That's all that's left. And you'll see here, when we subtract the indices, we also get 2 as our index. So that's why the law works. So here's another example, this time with division. Once again, we do the same process with multiplication, except for that one step. Work out the basic numerals or coefficients first, so our 12 and our 3. Then subtract the indices. So here we have 12 divided by 3 in green. That's going to be 4. And we subtract 2 from 6 because of the index law. We're dividing. So that gives us 4 for the coefficient and e to the power of 4. Here's another example. This one is a little bit more complex in that it allows us to combine a couple of the rules together. So let's look at what that does. When you've got multiple expressions or items on the numerator and multiple expressions or items on the denominator, it's often recommended to work out the numerator separately and the denominator separately and then try and put them together. So let's see how we go. In this case, the only common things on the numerator and the denominator are the coefficients, so we can work them out. One of the tips we should do though is try and cancel out common factors to make the numbers smaller. So as you can see here, what we have here, the 8 and the 4 both have a common factor of 4, so we can divide through by 4. 8 divided by 4 is 2, 4 divided by 4 is 1. Over here, the 25 and the 10, they have a common factor of 5. So if we divide 25 by 5, we get 5, and 10 divided by 5 gives you 2. Like that, and we're left with these numbers. So we can calculate that fairly easily. We can also cancel those 2's there if we like, giving us a coefficient of 5 total. Okay, or 5 times 2 is 10, divided by 2 times 1 is 2, so 10 divided by 2 is 5. Now you could just use your calculator and work that bit out using your calculator. So now we've got our V's and our W's grouped together. I've highlighted each of the indexes that match with the same base in the same colour. So this is what we're up to. From there, that's our coefficient calculated. We subtract the 2 V bases because they are the same and we're dividing them, and the same with the W's. So our final answer is 5, let's go back, 5v squared w to the power of 4. And remember, we don't need those multipliers if we don't want them. Another example. This one here has got 3 expressions, 1 in the numerator, and 2 in the numerator, 1 in the denominator. It is possible to work it all out in one step if you like, but once again, it's recommended to do it in multiple steps if you're having a bit of trouble. So here we go. I've highlighted the coefficients in blue. I've highlighted the indices in green with the same base of t. Cancel the common factors again. So 4 and 12 have a common factor. So 4 divided by 4 is 1. 12 divided by 4 is 3. And it's going to make the numbers a bit easier to do without a calculator. It's a good habit to get into and practice to get into. Try and solve these sorts of questions without your calculator. So they cancel. There's the cancelled down terms there where we divide both of them by 4. We're adding the numerator, 3 plus 8. If you wanted, you could also do the subtraction there and take 4 and do it all in one step. So we get 7t to the 11 over 3t to the 4. Now 7 and 3 have got no common factors. We could write that as a decimal, which is 2.3 recurring. But it's best to leave it as a fraction because it's more accurate. If we apply our index law there, we're subtracting because we're dividing the 2 bases. So 11 take 4 as our new index. And our number becomes, our expression becomes 7 thirds, 7 over 3, multiplied by t to the power of 7. And that's the best way to represent it. An alternative, you could write it as 7 thirds multiplied by t to the 7 instead of all over 3. They mean the same thing. So now on to our third index law. This is the zero law. And it's probably the easiest one. So we're going to start off with a basic number pattern. There's 10. 10 is also 10 to the power of 1, or 10. As we multiply by 10, we're adding 1 to the index there. We're also moving the decimal place 1 place to the right, which increases the number of zeros in the number. So that's 100. Repeat this pattern, 10 to the cubed, 10 times 10 times 10, and 1000, and so on. So like I said, as we go up, we're multiplying by 10. Now if we go the other way, the opposite direction, we're doing the opposite operations. So here's 10 to the 0. What we do as we go down is we're dividing by 10. So from there to there, we're dividing by 10. That's what happens when you reduce the index by 1. So we're taking 1 from the index to get 10 to the power of 0. 10 divided by 10 is 1. And so on. And we'll look at this other line here a little bit later. So as we go down, you divide by 10. Any base, no matter how complicated or large, with an index of 0, always equals 1. That's all you need to remember. So you can have heaps of things inside a bracket. If that power of that bracket is 0, your answer is 1. So that's your rule. A for anything to the power of 0 equals 1. So here's an example. Like I said, no matter how complex that expression is, all of that's in a bracket to the power of 0. So the answer is simply 1. Here's a more complex one. So this is actually going to combine all three of our laws together. Once again, evaluate the numerator and the denominator separately, particularly if you're having a bit of trouble. So here our coefficients 9 times 4 on top, 6 times 2 on the bottom. They have some common factors, so we're going to be able to cancel down. And I've denoted the indexes in green. We have the same base for all of them. So let's cancel down. 9 and 6 have a common factor of 3. So that means this becomes 3, and this becomes 2. 4 and 2 have a common factor, so that's going to become 2 and 1 when we divide by them. So 3 times 2 over 2 times 1, those 2's also cancel, so if we like, we can cancel them out as well. Go add the indexes at the top and the bottom, and we get this, 6 times 2 times g, 11 on top, times g, 11 on the bottom. So we're dividing, so we're going to subtract those indexes. So 11 take 11, 6 divided by 2 is 3, giving us 3 times g to the power of 0. G to the power of 0 is 1, so this becomes 3 times 1, or 3. So that whole expression which we had right back here, actually here, equals 1. And that's why we teach these sorts of skills, to try and reduce the complexity of what you're seeing. So there's our learning goal. Hopefully we've met that. This is something that you really need to practice. The skills you've seen here in this short presentation are actually revision from grade 8. If you need more assistance, please contact.